All right, so today we're going to be doing day 17 in Advent of Code. The first part of this challenge is going to be that we're going to run a computer, sort of. And there's different operands that we can do, and there's different registers that we have, and we have to move the information back and forth and so on. And they give us the exact instructions of how the computer works. So the first important thing is that this computer is a 3-bit computer. So it works not just with ones and zeros, but with 0, 1, 2, 3, 4, 5, and 6 and 7. So if we just look at the input really quick, we can see that we will get a register, A, B, and C, and they will begin with something. And then you have the actual program, and this is what it's going to run. So there's a bunch of numbers, and there's always going to be an opcode, and there's going to be an instruction right after. So there's going to be the opcode 2 and the instruction 4, opcode 1, instruction 1, opcode 7, instruction 5, and so on and so forth. So they're always in pairs of 2. So if we look, what does opcode 2 mean? So if we look at opcode 2, they describe it as it calculates the value of its combo operand modulo 8, blah, blah, blah. These explanations are quite long, so I'm going to show the explanations that I've done in my code instead. So let's see. So for opcode 0, what we do is they call it ADV, but what we do is we just divide the register A by a power of 2, so 2 to the power of something, and if the operand is 1, 2, or 3, it will just be to the power of 1, 2, or 3. But we need a function getComboValue because they say, okay, if the operand is until 3, and they mention it, where do they do that? They mention it here, then just have it as whatever operand it actually was. But if it's 4, 5, or 6, then it should give us the value of register A, B, or C. And then apparently 7 should not do anything in any case. So that's what we do. We get the combo value. If the operand is less than 3, we just return the operand. If it's 4, we return whatever value is in register A. If it's 5, whatever is in register B. If it's 6, whatever is in register C. And if it's 7, we should return some kind of error. Then the first opcode, or opcode number 1, BXL, they want us to do a bitwise XOR of B and the literal operand, meaning this actual operand. And we can either say register B is equal to, and then we bitwise or this and operand, or we can just say this sign over here, which means that we do a bitwise OR with this, and then place it inside here, which is what they want us to do. Then we have BST, which is to get the combo value of the operand and put it inside B. And we always do modulo 8 because, for example, if we somehow have to read what's in register A, then, for example, here it's really big, so it's going to be hard to calculate with these numbers. So they just do modulus 8, and then we put it in some other place. Then opcode 3, this is an interesting one. We have jump. So if we're currently reading over here, and then we read here, and then we can see at the end there's a 3, 0. So what this means is jump to the 0th place. So we're going to jump all the way to the beginning and keep reading, and then do it again and again and again. So how do we actually stop? We only stop if we see that what's in register A is 0. So as long as register A is not 0, we will keep jumping to the beginning, because we set the operand to the pointer, and the pointer is 0 to begin with, but it increases every time by 2 because it's in pairs of 2. We always get the opcode and the operand together. Then opcode 4 is BXC, as they call it, or a bitwise XOR, exclusive OR of B and C. So exclusively where there's an OR, where this one's a 1 and this one's a 0, then it's going to return a 1 and put it in that bit place, and it's going to do that with every bit of B and C, and then put it inside B. Opcode 5 is going to be out, and this is also an important one because it actually outputs the value. So we get the combo value of the operand modulo 8 again, as they want us to do, and I just append it to the output, which I will keep for later. And then later we will be printing all of them out. Then opcode 6 is BDV. So what we do is we divide A by a power of 2, and then we do it again, operand and get combo value. And when we divide, we always do 2 division signs, which means floor division, because we don't want any floats or anything after the decimal. We just want how many times it fits. And we set it to B. And in the 7th case, it's the same thing, but we set it to C instead. And otherwise, we should just raise an error, but this should never actually come up. Some of my friends had different inputs and they've never gotten these errors. And that was explaining how the opcodes work, so the actual requirements that they've asked us to do, and then there's some examples in here as well, and some lore, and then we're supposed to answer with commas in between whenever we get the answer. So this is the actual program, and then to just get the input, so I've put everything in input.txt over here, and then I read all of the lines. And what we can do, since we can see, okay, register A, B, C are on line 1, 2, 3, and then program is on line 5, we can just read the line 0, 1, and 2 into register A, B, and C. So here's where I define the registers. Then we can parse the program to get the actual program instructions, so these numbers, but we have to get rid of the program 2 dots over here. So I search wherever there's 2 dots, I take whatever is left on the right side, so we take this and we strip any weird characters, and then I iterate through it, and when I split it by the comma, because we can see between every number there's a comma, so I iterate through every value and I append it as an integer to the program. So now we have a list of all of the numbers that are actually the program that we're supposed to run. And then we have the get combo value, of course, which I've shown, and this while loop, it iterates as long as the pointer is less than the length of the program. And as we saw, we can reset the pointer, so then the while loop keeps going, and we always go in steps of 2, so we get the opcode and operand at the same time. And once we've found the right opcode to execute, then we add 2 to the pointer, of course. Then once we've added enough things to the output and everything has ran, and the program has actually finished, so whenever this opcode 3 is called and then A is 0, then it's going to break, because it will go pointer plus 2, which will be bigger than the length of the program, so it will break. Then I want to actually print what's going on, and the reason that I'm doing this for value and output and then making the value into a string is because if we just say string to this output, then since it is a list, then it's going to look very weird, but technically still the correct answer. But so we can see this is the list, but it's going to take every character in this list and then put a comma in between it. So comma join every character in this list. So it's going to put a comma in between the parentheses and between the 7 and between the comma and between the space and between the 3. So it's going to look very weird. So instead what we do is we just iterate through every element, and then when we iterate through the element, we just get the number itself. We make it into a string and we append it to string output, which I just join with commas. And when we run this now, we get this nicely formatted answer, which we can just copy, and it's 730-571-405. And we can see that that is the correct answer that we get. So that is the output of part 1. So now for part 2, it's basically the same thing, but what we want to do, instead of seeing what the output is, we want it to get the exact same output as the input, given that we can change whatever register A has to begin with. So if this is what register A has to begin with, then we will get some kind of answer. But if we set this to register A, so if we do this really quick, if I copy this as the example, and then I put it in the input, and instead of whatever they gave us here, we put this and register A. And then since we have the this program, we can just run it, and we can see it outputs 035430. And that is exactly what the program was to begin with. So it outputs the exact same thing as the program is. So that is our goal, but not to do it with this sample, but to do it with whatever the original thing was that you get. And for every user, it's a different puzzle input. And the only thing that we're allowed to change is what register A was in the beginning. So we can either iterate through every possible register A, but you can see how big my answer was, and that's not feasible. It's going to take forever. Or you can sort of reverse engineer every step that it takes, and then sort of go backwards and see what's happening, and then try to get to whatever A should be, what's a valid A, to be able to print the exact same numbers in the same order. And there's a word for this type of program, and it's a Quine. So a popular Quine program is the donut, and it's not exactly a Quine program, but it's in the shape of a donut, and then it prints a donut, and it also spins, which is kind of cool. But if you can call this a Quine program, then you can call this a Quine program as well, since it prints whatever this part is, it prints the exact same thing as the output. But an actual Quine program would be if you take the entire file and you run it with the code itself, so every definition, every function, everything, when you execute it, it should output the exact same thing, the exact same file. So it's not just one part of it that should be outputted as the same, it should be the entire file, not just the input, but the actual code itself. So that's a lot more difficult to do, but this is sort of making a part Quine program. So if we can look into part 2, we have the same type of opening the file, and we parse it, but now we don't actually need the registers, since we're going to be backtracking what the registers should be, so that we can output what the minimum value in the A register can be. So we just get the line 4, and since it's from 0, that's the 5th line, so we just get the programs, we parse them, and we put them in the program. And we have to make some assumptions, actually. So I've looked at some of my friends' inputs, and it seems that all of them end in 3-0, so that's a good sign, because it means that, okay, we're going to keep jumping back, keep jumping back, keep jumping back, because if we would never jump back, then the only case in which we print something is when we add it to the output, so that's at opcode 5. So that's the only time that we actually print something. So if there was only one opcode 5, so let's say this is 5.4, then we would only be printing, it's not actually 5.4 because this is 7.5, but do we have any opcodes that begin with 5? Yeah, it's this 5.5 here. So if there was no jumping back, then we would have to have a lot of 5.5s, and then we would never be able to print as many 5s as there are, because there will be twice as many 5s as we are even able to print something. So we have to have some sort of jump somewhere, and we're assuming that there's only one, because if there was 2 of them, then we would have to sort of branch everywhere where there's a jump and then check both sort of cases, and then it would just get a lot more complex. But based on the inputs that some of my friends got, it seems that it always ends with 3-0. So that's one assumption that we make, and what we do here is we just check that the last 2 elements should be 3-0, and if it's not, then we just raise an error. Then we have the same combo operand evaluator, and it's the same thing, but I also give it the registers, and the reason that I do this is because in the solution I've done it recursively, and every time that we call this function, we might have different registers because we're in a different step of the recursion. So I want to give it whatever registers we currently have, so we define it inside here, and then whenever we give it to the get combo value, we send it the current registers of whatever recursion step we're into right now. So what we do, since we can see that there's only one point where we write to register A. So if we scroll, we can see that it's only opcode 0 that actually writes something to register A. So register A is equal to something. But if we look down, nothing happens with register A. Here we only check if it's not 0, but we don't actually change it. So the only case where we change register A is where we see opcode 0. And we have one here. So another assumption that we need to make is that there is an opcode 0, so that we do write something to register A. Otherwise, well, we couldn't get to 0 and the program would never stop. And the third assumption is that this opcode 0 has a 3. Why? Because 3 means that we're going to divide it by 8, and dividing it by 8 is the same as bit shifting it to the right by 3. So here, if we have some bits and their significant values, if we have number 15, this is how you would represent it in bits. So at the value 1, it would be a 1. So 1 plus 2 times 1, which is 3, plus 4 times 1, which is 7, plus 8 times 1, which is 15. So that's how you represent 15 in bits. Now, if we bit shift by 3, so we go to the right, and then we move everything to the right, then these ones just disappear, they're gone. these three ones over here, but this 001, it will be like this 001, and then the 001 just means that it's a 1. So the 15 becomes a 1 whenever we do a bit shift. So since this is what we're doing, we're sort of removing information. We're just plopping this into the void, so it disappears. So what we have to do is we have to sort of iterate through the range of 8, and we have to check all of these different branches and see which one was the valid one, because we've lost some information when we've gone forward in the program. But if we're trying to backtrack and get to the original answer, we have to check every possible combination, and that is a combination of 8. So what we do is we bit shift to the left into the answer, and we bit shift the t, which should be 3 bits. And the b and c we do nothing with, we just initialize them as 0. So we also have to assume that they're 0, but it seems to work like this. Then we have the same type of loop where we just loop over the pointer. But in this case, we only do it until -2. So we don't actually check the last 2 inputs because we assume that they are the stop. And at opcode 0, we have to make sure that we haven't found it twice, so that we haven't found ADV twice. So the way that we do that, if this is false, so it begins as false, then okay, it's fine. If the operand is not 3, which we assume that it should be, then we say that we encountered an invalid operand. What we can do if yours somehow is 4 or another number is you can change this t into the 4, and then it should work. But if we encountered it once, then this becomes true. So next time that we encounter it, we will return an error, which is not good. But since it should only appear once, it should be fine. Then for operand 1, what we do is basically the same thing. So we can see operand 1 is registers B, and then bit shift bitwise XOR with the operand. So we do the same thing. And then get combo value, but we also send it to registers because we want the current ones of the current recursion. And we do basically the same things, except for number 3. When we jump, we shouldn't actually jump ever, because that's the last place that we never check, because the range is until -2, and we step in steps of 2. And everything else is pretty much the same, and of course we raise this, but it should never raise this error. And then whenever all of these different pointers have ran through, so when the program has ran through, if the output is what we should get, if the target, which is the target, so the last element, so in this case the 0, then okay, great. We call the same function again, but we only give it the same targets until -1 non-inclusively, so we give it a smaller target now. So we keep giving it almost all the targets except the last one, and then whatever the value for the current register A is. And we can see that in the beginning, when we called the function first, we gave it 0 as the current value to register A. So we begin with 0 because we know that's when the program ended, meaning that the value A was 0, that's why it ended. Otherwise it would not end. We can see here at opcode, which one was it? Opcode 3, if register A is 0, then of course it's going to stop. So we keep doing that, and we keep calling the function until it reaches this point. If there's no more targets, then we just return the answer. So if we've cut off all of the numbers one by one, then we've reached a recursion depth of how many ever digits there are. And then when we have no more targets, we just return the answer, which is the current A value. So we recursively return everything. It returns, it gives us the sub result, it returns, gives us the sub result, blah, blah, blah. Keeps doing that until finally this actual the first time that we called this find solution also returns something, which is the solution itself. So when we run this, we see that it takes a second to run, but this is the number that we get, and it's a really big number, and it would never work to do this by brute force. So 202972, let's see if it's correct. So 202972, and it seems to be correct. So that was part 1 and part 2, and how to solve it, and it should work for everyone's input, even though it's different for everybody. And if it doesn't, then let me know in the comments. And now for the time complexity of part 1. So we have n as the number of instructions in the program, and of course this can be more than just I don't know, 15 or how many ever instructions there are here, because we can jump. So if we jump 100 times then to the beginning, then it's going to be 15 times 100. So if we just say that that's somehow we know how many instructions there are, then the time complexity is just O of n, which is great. And then the space complexity would be the same. It's not actually as much, but we can say that it's O of n. And for part 2, it's not that similar actually, because we're doing it with a recursive function to backtrack everything. So we have the n, the number of instructions, m, the branching factor, which is 8, because we lose some bits of information when we go forward. So we have to backtrack and check, okay, which case was right, which case of the branch was correct. So we have to do each recursive time that we call it, we check 8 different times. So the time complexity is m times d to the power of n. So in this case, it's 8 to the power of d times n. And d is the recursion depth, or the number of digits that we are expected to print. So not too bad, since d is not too big, and m is just 8, so it's not too bad. But this is, in my opinion, the best way that you could implement this. And then the space complexity, it's pretty good. It's n plus d, so just the number of instructions that we have, and then the recursion depth to keep track of the recursion stack. So that was the time complexity of part 1 and part 2. And now, if you guys want to join the leaderboard, I will leave the code in the description. And yeah, thank you for watching. Happy holidays, and see you tomorrow.